Hello everyone. I wanted to remind you of a definition, analytic. We say a function is analytic at a particular number if it is infinitely differentiable at that number, meaning quite simply that the derivative exists for every derivative you take, where n is the second, third, fourth, fifth, on and on and on. So a simple example, if I considered the exponential function, because it's defined everywhere and all of its derivatives are defined everywhere, we'd say it's analytic everywhere. Then if we take something like the cube root function, it's defined everywhere, but every derivative has an x in a denominator, therefore it's not analytic at x equals 0. Now let's consider our generic differential equation that we've been working on. Okay, if I consider this guy right here, and I multiply through by 1 over a2, I will get the following form. Where the p of x is simply a1 over a2, and q of x is a0 over a2. Now, we'd say that if p of x and q of x are analytic at x equals x0, then x equal x0 is what we call an ordinary point. Okay, so meaning basically, if I have x's to a power here, then at this point here I'm going to have x's in the denominator, so x equals 0 would not be an ordinary point. But if I don't have x to a power in front, then I can easily expand this about x equals 0, which is what we've been doing. Okay. Now we want to talk about what's called a singular point. So going back to the form we just did, okay, if x0 is not ordinary, then it is a singular point. But now there's two types of singular points. Okay? The first one we're going to describe as what's called a regular singular point. A regular singular point is one in which x minus x naught times p of x and x minus x naught squared times q of x are analytic. Now that seems a little bit confusing, but basically it means that if the exponents aren't too high in the denominator, these terms would cancel and I would get what's called a regular singular point. Now if it's not a regular singular point, then it's called an irregular singular point. So let's do a couple of examples. So first example here. I've got x cubed, x minus 1, plus x squared, plus 3y equals 0. Now clearly if x is 0 or x is 1, we have a problem because these guys are going to end up in the denominator. So we can see that x equals 0 and x equals 1 will not be ordinary points. They will be singular points, but we have to figure out what type. So the first thing we do is multiply through by the reciprocal, in which case I will get something of this form. Now the idea is, if I multiply through by x on this one and x squared on this one, if I eliminate the x, then it would be a regular singular point. But this exponent here is too large. So x equals 0 is an irregular singular point. Now if I multiply this one by x minus 1 and this one by the square of x minus 1, the x minus 1's would be eliminated, so x equals 1 is a regular singular point. Again, all I really have to do is look at the exponents. If these exponents are less than 2, then I'm okay. If these exponents are less than 3, then I'm okay. Now let's do another example. Let's try x squared plus 1, x squared minus 1 squared. No, but here you say, well, x squared plus 1 is never 0. Well, actually, it is at plus or minus I. So plus or minus I and plus or minus 1 would all be singular points. We just have to figure out regular versus irregular. So once again, we start by multiplying through by the reciprocal of this quantity. Now, it may be useful to look at x squared minus 1 as a product of conjugates. So that's actually going to be x plus 1 squared, x minus 1 squared. So when I multiply through, I will cancel with one of these, and I will get 1 over x squared plus 1, x minus 1 to the first power, x plus 1 to the second power. And then the last term, something similar I'll write down here. I'll get x squared plus 1. Then I'll get x minus 1 squared and x plus 1 to the first power. So as I analyze, I've got x equal I, x equal negative I, x equal 1, x equal negative 1 potentially. Now because this is going to just produce an I and a negative I, and this same thing here, these will be regular singular points, both of them. Now over here, the exponent on this one is good, but this one is too many. It doesn't have to fail both, it just has to fail one. So x equal negative 1 will be an irregular singular point. Now x equal positive 1, the exponent is right here, and it's right here. So this one will be a regular singular point. So our main goal is to identify these. The algebra is actually quite simple, but the conclusion is very important.